Good morning everybody. Welcome to this class on the DD transitions. So we'll be talking on the corresponding electronic transitions, what we can have, and we can measure nicely using a spectrophotometer, and we can basically characterize. So this is one of the most important characterization data what we can have for the transition metal complexes. So if we have several such transition metal complexes, and we should all be looking for the characteristic transition frequencies, that means the corresponding energy of these transitions. So that will also tell us that what type of transitions we are considering. So we can have several types of such transitions, and if we consider, say, several such species, including the metal salt, which we can dissolve in water to get the corresponding species immediately, such as hexac or titanium 3 ion, which can be derived very nicely from the corresponding titanium chloride salt. And when we make the solution of this particular species, that means since we are dissolving in water, so it is a solution in water, and we can have the corresponding multi-electron system for this one if we have more than one d electron for this particular ion. So we basically see that when this particular complex is exposed with some blue green light, so wavelength corresponding to the blue green light, and the electronic transition will take place at that particular point at 493 nanometer. So this particular blue green light corresponds to this particular wavelength, and in wave number unit this corresponds to 20,300 centimeter inverse, and the corresponding color of the solution, which would be purple violet, what we see the corresponding complementary color, and this would definitely be the corresponding color of the ion or the complex ion. So this is the color of the complex ion. So at this particular wavelength the absorption is taking place, and we will see the corresponding color. So for these as well as for some other compound, when we just simply change, because the crystal field explanation what we can have for color change in any complex is due to the change in the corresponding ligand environment. So from 6 water ligands, if we go for 3 bipyridine ligands giving same octahedral coordination geometry, because the symmetry for this d electronic configuration is also important. We will see in some moment that it is very much dependent on the corresponding symmetry of the species. So now we exposed this with violet light compared to this blue green light. So violet light will be shaded on this particular ionic species, which is of high energy compared to this one, and definitely once we state that this is of high energy, it will be shorter in wavelength compared to this 493 nanometer. It will be in the range of 400 nanometer with a corresponding wave number value of 25,000 centimeter inverse, and the corresponding complementary color, that means the color of the solution what we will be observing is yellow green. So for this particular species and other species like that of that cobalt compound, say, because large number of metal complexes we can handle by measuring the corresponding lambda max values and the epsilon max values. So the data what we will be reporting for all these complexes will be the corresponding lambda max, that means the maximum absorption wavelength, and the corresponding molar absorptivity at that maximum value. So this particular compound, if we just compare with that of our well known hexaamine cobalt 3 chloride compound. So you have CONH3 whole 6 Cl3, and this compound is high spin and this is low spin. So electronic transitions will take place at different wavelengths. So in this particular case, since it is high spin in nature, so it will absorb low energy light it will definitely absorb the low energy light and therefore transmit the corresponding high energy light. So this particular compound, therefore when it is high spin, the color is blue, but this one basically is a low spin one and its color is yellow to orange, and here the absorption is taking place not at low energy but at high energy. So high energy light is absorbed and definitely the transmitted light would be of low energy and it emits low energy light. That means these two combinations, that in one case the absorption at low energy and in another case absorption at high energy, clearly distinguished these two forms of these complexes. One is high spin and another is low spin. So in case of high spin, it absorbs low energy light, that means delta octahedron for the high spin species is less than that of our pairing energy. We already discussed all these things again, but when we experimentally determine the values for the corresponding absorption, we should immediately be tell about that definitely this is the corresponding compound which can form the high spin species, because in case of cobalt 3 only this compound and other the trifluoro analog of this with 3 water molecules are only the known high spin compound, the rest all are low spin compounds. So this is the situation for the high spin compound, and the reverse is therefore, that means delta O for low spin is therefore greater than the pairing energy. So if we just these two things we can compare, we will find that the delta O of low spin will definitely be greater than delta O of high spin. That means there will be a change in spin states when we change the corresponding delta values, and in terms of the spectroscopic signatures we will find that the different amount of energies, different amounts of energy are required for the electronic transitions in the two spin states. So, if we have two spin states, one is low spin and another is high spin, so definitely their corresponding lambda values would be different. So, that basically gives us the corresponding idea for these transitions. So, what about these corresponding transitions, what is taking place based on this cobalt 3? It can be in the high spin or it can be in the low spin state. So, cobalt 3 ion in high spin and in low spin state, we have unpaired electrons in one particular d level, and the upper available d level in terms of the corresponding crystal field theory, that the upper level is also of d character. So, the transition what is taking place from one d type orbital to another d type orbital, that is why we call it as a dd transition. But through some selection rules and all these parameters what can control the corresponding transitions, we will find that these dd transitions are not very much allowed. That is why the corresponding intensity of these transitions are weak. So, whenever we find any weak dd transitions in metal complexes, how we can utilize for these characterizations we will see. So, we will have weak dd transitions. So, we will be using some mathematical concept of even and odd functions. These functionalities are related to the corresponding type of the d orbitals, whether it is dxy orbital or dx square minus y square orbital. They can be considered, or some s orbital or p orbital. So, we have the even and odd functions related to these transitions, which can be controlled by the corresponding rule, which is known as Laporte rule, and the Laporte rule is derived from that mathematical concept of even and odd functions related to the dd transitions. So, when the electronic transitions will be taking place from wave functions with G symmetry to wave functions with another G symmetry, that means G means the even symmetry, are forbidden. So, this particular thing, that means the symmetry controlled thing, that means when the even symmetry orbital is allowed for transitions to another symmetry related orbital is forbidden, as are the transitions from wave functions with uneven symmetry, that means the U symmetry, to the wave functions with again U symmetry. So, with respect to the center of inversions, we have seen that the sum of these orbitals will be labeled as having G symmetry and another will having U symmetry, such as we have two types of orbitals in centrosymmetric OH symmetry, that means the octahedral symmetry. We can have the T2G set, which is G type, and another is EG type, which is both are of same symmetry. That means this transition will not be allowed from T2G to EG. Similarly, if we can have a T1U symmetry to T2U symmetry or T1U symmetry, that will also be forbidden. But the transitions from G to U and U to G, where the symmetry switches or the symmetry changes, may be but not necessarily allowed. So, it can be relaxed only when we have G to U transition or U to G transition, that can be allowed to some extent. So, how and what are the different types of dd transitions we can have for certain metal complexes bearing unpaired electrons in 3D level, 4D level or the 5D level. So, we can have the pi donor ligands. So, these pi donor ligands lie lower in energy than the pi acceptor ligands. So, the energy leveling for these different types of orbitals, most of the time we are considering the corresponding sigma donor only orbitals. That means the sigma donor ligand, that means the water molecule and the ammonia molecule. But there are some other where the pi donor ligands are available and the pi acceptor ligands are also available for donation as well as acceptance of the electronic charge density from the metal ion. So according to the spectral chemical series or the spectrochemical series, one can determine whether the ligand will behave as a pi accepting or pi donating. So depending upon the mechanism of electronic charge transition, we can have some ligand as pi acceptor ligand and some as the corresponding pi donor ligand. So this spectral chemical series or spectrochemical series, one can determine whether the ligand will have a pi accepting or pi donating one. When the ligand is more pi donating, its own orbitals are lower in energy than the T2G metal orbitals. So the ligand will have one orbital which is pi donating, so it will be lower lying compared to the T2G metal orbital, forcing the frontier orbitals to involve an antibonding pi star and an antibonding sigma star level. So we will have the different types of orbitals which are available depending on the donation from the metal as well as the ligand. So these DD transitions denoted above by delta for the pi acceptor ligand complex is larger than the pi donor ligand. So we just can modify this DD transition. So if we can have one particular level which is EG and another is T2G, they are not symmetry allowed for the corresponding electronic transitions, but if we can have these are of pi type because they are intermediate between the metal ligand axis, but these are of sigma type. So this is sigma type and this is pi type. And if we have the corresponding ligand orbital somewhere here, so this ligand which can be our pi donor as well as pi acceptor. So the positioning of the pi donor ligand and pi acceptor ligand will be different, and due to that we can have not only this T2G type or pi type orbital, we can have the corresponding pi star level as well as for sigma we will have the corresponding sigma star level. So involving all these we can have the corresponding transitions from one level to the other. So if we see the DD transition of pi accepted ligand to be of higher frequency than the pi donor ligand, so we just compare that how pi acceptor ligands can be compared with the pi donor ligands. So how the energy levels, the energy of these two levels, that means E1 and E2 and the delta E values are getting modified from the nature of the ligand basically. So ligand can modify the corresponding energy for these electronic transitions. So these transitions appear as weakly intense on the spectrum because they are all Laporte forbidden. So we will see what is the Laporte rule and how Laporte rule can be controlled. Even if we have so many of these types of levels, that means the ligand pi donor or pi acceptor and the metal ion sigma pi as well as pi star and the sigma levels. But some relaxation is definitely be there. In true sense, mathematically we can say that Laporte rule will not allow these DD transitions. But due to some coupling which we call as the vibronic coupling, and the vibronic coupling is nothing but if we have a metal center like this where we find that 6 ligands are attached to the metal center. So 6 ligand groups are there, and if it is in octahedral symmetry, we have the corresponding center of inversion which is located at the metal ion and through which we can interchange these are ligands L1 to L2 or L3 to L4 and so on. So if this is there, and now since all the time this covalent bond or the coordinate covalent bond between the metal and ligand, they are under thermal vibration. So, this metal ligand bond are compressed and stretched depending upon the corresponding vibration, and once you have the corresponding unsymmetrical vibration, that means this bond is getting longer and this bond is getting compressed, so I will be lost, and due to this vibration we have one mechanism which is known as vibronic coupling, and this vibronic coupling is responsible for the destroying the corresponding asymmetry, and once the asymmetry is lost we will get some amount of relaxation for the corresponding G to G or U to E transition, which is otherwise Laporte forbidden. So, due to this vibronic coupling we have little bit of relaxation of these rules, and they are therefore quickly allowed, and therefore the corresponding energy for the transition is very low, and they can only emit visible light upon relaxation, which is why many transition metal complexes are brightly colored, because we see this in the visible light range, but the molar extinction coefficient for these transitions are very less, which is around 100. That means the epsilon max, which is in the order of 100 only, because the corresponding absorption values in the y-axis for the electronic spectrum is less. So, if the integrand of the transition moment integral, which we find from one level to the other, we find the corresponding transition moment integral contains the totally symmetric representation, which is related to the symmetry from one level to the other, then the transition is Laporte allowed. Then only this particular transition will be allowed and we get right intensity or maximum intensity for that particular transition. And if the transition does not contain totally symmetric representation, then the transition is Laporte forbidden. So, symmetry as well as group theory plays an important role to identify these symmetric representations, which are either centrosymmetric or not symmetric with respect to the transition. The totally symmetric representations in the irreducible symmetry representation, that means this A type of representation, that is even with respect to all symmetry operations. That means some symmetry representation we can have from the corrected table of the corresponding symmetry group, which is in this particular case if the metal complex what we are considering is of OH symmetry, then we perform some of the symmetry operations, and with respect to these operations the irreducible symmetry representation should be even due to that symmetry operation, and on the corrector level these representations are usually listed first and has the designation either A, A1 or A1G. So, these are the totally symmetric representations what we can find typically from the corresponding corrector table of the symmetry point group. Then we see that what we call as the corresponding selection rule, because this selection rule will be controlling the corresponding transition from one level to the other. So, first of this is the corresponding spin state. That means if we are considering transition from one particular metal ion, say if we are considering one particular system where we have the T2G and the EG level, which are of these. So, we have the T2G and the EG level, and we can have, say for chromium system we have 3 unpaired electrons, and these 3 unpaired electrons will giving rise to a total spin value S is equal to 3 into half is equal to 3 by 2. So, considering these 3 unpaired electrons, that all the time when we measure the corresponding magnetic moment, we should get the corresponding magnetic moment for these mu effective values for 3 unpaired electrons. And when we find that 3 unpaired electrons are still there, and we get a total S value equal to 3/2, and the spin multiplicity, which is the number of arrangements what is possible with this many number of unpaired electrons, would be equal to twice S plus 1, which is 2 into 3/2 plus 1, that means is equal to 4. So, 4 different types of arrangements are possible when we have these 3 number of unpaired electrons. So, due to this transition, if we can move this electron to the upper level, we still have 3 unpaired electrons from these 3 levels, but the transition has been taken place from T2G to EG, that means 1 unpaired electron has been moved from this T2G level to the EG level. But for that state, that means when we have 1 electron in the excited state, that means in the EG level, we still have 3 unpaired electrons. So, our spin multiplicity value is still 4. So, if we consider one particular transition, that means where we can have the corresponding transition from a spin multiplicity value of equal to 4, because we will get some term symbol for multi-electronic configuration where we write on the left superscript, as left superscript is the twice S plus 1, that means the spin multiplicity value which is not changing. That means we can have one transition from a 4 spin multiplicity 4 state to another state having the same spin multiplicity, then that is allowed, which is the first rule from the Laporte selection. And since both are preserved as the corresponding spin multiplicity value equal to 4, that means S values are not changing from the ground state to the excited state due to the electronic transition. So, our delta S value would be equal to 0. So, we do not expect any change in the spin values. That means this up spin, when you move it to the upper level, should not be the down spin system. If it is down spin, then it will reduce the total spin value as well as the corresponding spin multiplicity value. So, the first of this in the Laporte selection rule would be therefore delta S equal to 0. And the second one is that DD transitions are forbidden transitions if the delta L is equal to plus minus 1. But the Laporte allowed transitions is the change in the parity occurs, that is if we have the corresponding transitions from S level to the P level and P level to the D level. So, these are Laporte allowed transitions, but what we are talking here is the corresponding DD transitions in the electronic spectra, that would therefore be only Laporte forbidden transition. So, the Laporte forbidden other transitions would therefore be the same way the parity remains. When the parity remains unchanged, that means the PP transition and the DD transitions are Laporte forbidden transitions. So, why we get these transitions even it is a very weak one? The DD transitions result in weak absorption bands, and most D block metal complexes display low intensity colors in solution. That means our epsilon max values are less, exceptions for D0 and D10 complexes where we do not have to consider the corresponding DD transition. The low intensity colors indicate that there is a low probability of a DD transition. That means the probability of transition is very less, and we get therefore a very low value of the corresponding epsilon max, and the transition moment integral is also very small. So, these rules are next can be relaxed by molecular vibration and spin orbit coupling. So, one we have seen that if there is a molecular vibration along the ML bond axis, and if they are destroying the corresponding symmetry, the inversion symmetry level for the system, and in other case if we have some amount of coupling between the spin moment and the orbital moment, then we have the corresponding spin orbit coupling. So that spin orbit coupling also can relax this particular Laporte rule. So the set of rules what we can have now, that GG is forbidden. So G by G transition, so G product G is also G, and U product U is also G. So these are two forbidden transitions, but G to U the product is U, and U to G product is also U. So in these two cases, when the products are U, that means uneven or odd, they may be the corresponding allowed transitions. So transition between two even states and two odd states are forbidden. So this is the rule which we get from there, that for two even states and two odd states are forbidden. So if the d orbitals in the octahedral symmetry having I, whose are corresponding symmetry level is there, that means the inversion symmetry is there and the system is centrosymmetric, and the excited state is also of the same type, then we don't expect any kind of transition from one even state of G type to another even state of G type. And also the rule also tells that does not state that transitions between an even and odd states are allowed. So this is some kind of only relaxation, that it is not telling at the same time that the transitions between the even and odd states are allowed. So it is not clearly mentioned. So now we see that what type of transitions and the corresponding transition probability can be inferred from the different type of transitions we can have. So we have taken 4 exact examples for these, and these examples will tell that there are 2 rules. One is related to the spin and another is the corresponding Laporte rule for the corresponding type, that means whether we have the PP type or PD type. So if we take the example of simple hexa-aco manganese 2 ion, it is a system of 3D5. So if we have the corresponding transition of this type, and if the one state to the other, so is a multi-electronic system, we have the corresponding term symbol and the corresponding electronic state which is required for the corresponding transition. So we have the ground electronic state to the excited electronic state, and the corresponding transition. So in case of this compound, the manganese hexa-aco 2+, it is very weak in intensity and very lightly colored, because the upper available level, the corresponding electronic level, which will have the different spin multiplicity, and since it is DD transition, we can consider it as both spin forbidden as well as Laporte forbidden. So in this particular case only, since it is a 3D5 system which is high spin, we have 5 unpaired electron and the symmetry level is A only, capital A, for the ground state, but the other excited states which are having different symmetry level as well as the different spin level also, because the spin is also changing when we move from a D5 high spin system to some other electronic configuration. But when we move to another octahedral molecule which is also hexa-aco, which is nickel hexa-aco 2+, this will be 2+. In this particular case, the excited level is spin allowed, that means of same spin type, but again it is DD type of transition, so it is Laporte forbidden. So compared to this hexa-aco manganese compound, the corresponding intensity and the lambda max values, the corresponding transition intensity is higher because it is spin allowed. So we get the corresponding molar extinction coefficient values, it is in the log 10 scale, which will be close to this particular value. That means this value is very small. Compared to that, the value for hexa-aco nickel is higher. Similarly, the other case we get where both of them are allowed. Here both of them are forbidden, here is one is allowed, but in case of tetrahedral nickel complex, which is NiCl4 2 minus, so it is Ni Cl4 2 minus, and it has a tetrahedral symmetry group, point group, and inversion symmetry is not there. And if we consider the corresponding these two states, again the ground state and the excited state, they are of same spin multiplicity value, so it would be spin allowed. So this particular case it will be spin allowed, but since the other case, that means since again it is the DD type of transition, it will be Laporte forbidden, but the corresponding intensity is higher compared to the corresponding hexaco nickel compound. So in case of nickel, these two species can nicely be compared if we just simply go for this corresponding measurement for the corresponding electronic spectra. That means when any nickel salt, say nickel chloride or nickel sulfate, is dissolved in water, we get this particular compound, and then if we add certain amount of say hydrochloric acid or any other source of chloride ion, and in higher concentration, or sometime you can add some bulky organic cation, that means tetrabutyl ammonium chloride or tetraethyl ammonium chloride, and the corresponding this particular salt can be isolated as, if it is NBU4 tetrabutyl ammonium salt, then NiCl4 2 minus can be isolated as this particular salt. So this can be isolated also in this particular salt, and in presence of this acid or in presence of only NBU4, which is tetrabutyl, tertiary butyl, tetrabutyl, the butyl group is tertiary, and so tetrabutyl ammonium chloride addition will give rise to this particular NiCl4 species, and where the corresponding lambda max will have some certain value, but characteristically the epsilon max is higher compared to the corresponding octahedral compound, which is hexaaco. Then as we move towards the right of this scale for the molar extinction coefficient, which is higher and higher above 1000, which is due to the corresponding charge transfer, which is both spin allowed and Laporte allowed. So when both of them are allowed, which is spin allowed as well as Laporte allowed, we get the corresponding CT transitions, which we known as the charge transfer transitions, that we will discuss in detail how a solution of potassium permanganate in water is highly colored, which is purple colored, and the intensity of this is very high, and we can be able to detect a very low concentration from this particular compound. So we have this example we have seen, this is the corresponding hexaacomanganese 2 plus, this 2 plus is be here. So is the hexaacomanganese 2 plus, which is very weakly giving transitions, and in case of these two cobalt compounds, so cobalt compound, so this is very weak, it corresponding lambda max value. So experimentally when we measure this, like that of our nickel compound, we see that the corresponding intensity is much more, that means the color intensity is very high if we get the corresponding non-centrosymmetric complex, which is the tetrahedral complex. So going from a symmetric complex, which is hexaaco cobalt 2 plus, if we go for a non-centrosymmetric tetrahedral complex, which is tetrachlorocobaltate ion, we get that the corresponding values for the lambda max is also increasing, as well as the corresponding epsilon max, because in this particular case the corresponding absorbance value is above 1. You see this absorbance is quite high, is 1.25 or more than that. But in case of this is pretty low, is already it is magnified by 10. That means if it is close to 0.4, so 0.4 by 10 is 0.04 basically. So this value is pretty less. Sometimes to measure or identify this particular band, we have to go for a highly concentrated, even 10 times concentrated solution. So the response what we will be getting for this particular solution is good and fine, because we get the corresponding absorbance values well above 1. But to get the corresponding response for the hexa-aco cobalt compound, we should have a solution concentration which should be 10 times. So typically when we measure these electronic spectra, we go for different solutions preparation. So solution preparation is a very important step to measure the corresponding electronic spectrum. So initially we make a solution of say 10 to the power minus 3 molar, then we dilute it to 10 to the power minus 4 molar, and then again we dilute it to 10 to the power minus 5 molar. So for most of the DD transitions which we are observing here, which is having a low intensity, can be available with this concentration. So we have to have some concentration of this type, or it can be, even if it not concentrated 10 times, it can be concentrated 5 times to measure a corresponding significant absorption, such as what we just have seen in case of hexa-aco cobalt compound. And for these basically, since the corresponding transitions, that means the epsilon values are very high, these concentrations are useful for charge transfer measurement. Similarly, for low concentration detection is possible if we go down to 10 to the power minus 6 or 10 to the power minus 7 molar, we will go for the emission spectroscopy, that means the fluorescence and phosphorescence. So this basically gives us some idea that how the corresponding lambda max and epsilon max will be changing if we go from one compound to the other. And in this particular case, we have multiple absorption for this manganese hexa-aco compound, and is a highly concentrated one, and we have multiple absorption is the very low range region, that means in the UV region also. And this particular transition, that's the D5 transition, we can have all of them are present in the two levels, T2G and EG, and due to this excitation, that means we are moving one electron from this level to the upper level. So we are basically pushing one electron from here to the other level. So two orbitals are available in the EG level, which are dx square minus y square and dz square. So definitely following Hund's rule, we have to push the second electron in the paired form. That means the total S value and the spin multiplicity value is changing from left to right. As we have on the left is the high spin situation, where we have 5 unpaired electrons, but on the right hand side we have only 3 unpaired electrons. So during this transition, the ground electronic state and the upper excited electronic state will have different spin multiplicity. That means the transition, the Laporte selection rule tells us for a regular transition in this region, the corresponding rule is delta S is equal to 0. That means we don't have any spin state change. But here the spin state change is there, that means we have the corresponding spin forbidden thing, and that is why the corresponding intensity is very weak. So the transition though is there, but it is both Laporte forbidden as well as spin forbidden. Then we just see the other type, that is the next category of the molecules which can show corresponding response for charge transfer transitions. So how CT transitions we handle, and it can detect a very low concentration of the analyte. Why this is so? Because this epsilon max, which is very important, as the corresponding lambda max, which is in high energy region and is approaching close to UV range, because the energy gap for this transition is high, and since the epsilon max, which is say around 1000 to 10,000 or sometime very high up to 35,000 we can have, which is mole inverse centimeter inverse. This is also mole inverse centimeter inverse. So we see the corresponding contribution from the concentration, because the absorbance applying both the combined form of Lambert and Beer's law is epsilon Bc. From here we derive this epsilon. So if the epsilon value is pretty high, we can detect a very low concentration, because the concentration can be very less if the epsilon value is very high, and this is the corresponding path length for the cell, which is typically 1 centimeter. So there will be some balance between this epsilon and C. If the epsilon value is very high, the C can be very less. As a result, we get an appreciable amount of this absorbance. It can range from 0 to 4. So to get some appreciable amount of absorbance value, we can detect corresponding charge transfer band at a very low concentration. So that's why most of the analytical technique, such as identifying some unknown concentration of KMnO4, identifying some unknown concentration of potassium dichromate K2Cr2O7, or sometime potassium perrhenate, which is not colored, that can also be detected in the corresponding range, that means the corresponding UV range, and that basically gives us some idea that how we handle a very low concentration utilizing the corresponding detection of charge transfer bands. So if we see that for DD transition the color is dependent on that transition, but why some is it that some transition metal complexes are intensely colored in solution, but they do not have any d electrons, such as this KMnO4, where manganese is present in +7 oxidation state. Therefore, the electronic configuration on manganese is a manganese 0 system, which is 3D0. Since it is 3D0, we do not see any DD transition. So DD transition should not be there for potassium permanganate, but still this particular compound is colored to pink. So why we see the color? So not only potassium permanganate, there are also some compounds where the metal is also not present. So these are some solutions which are colored, which are not colorless. So we definitely have some transitions like manganese 2 compound, the exact or manganese 2 compound, which is a very light yellow to pink in color, but these are basically fullerene oxides. So Buckminster fullerene, the C60 molecule we all know, which is a carbon cage type compound, but when it is C60 or C60 oxide or another C60 oxide of different type and is a dioxide, we get the corresponding colored species in solution, but they do not have any d electron. And the solutions of this is C60 is light pink in color and the corresponding oxides are yellow to orange. And in C60 we have large number of carbon-carbon double bonds are present, where we have a football-like structure which having some pentagonal and hexagonal cages only. So, in this molecule, so this is also colored. So, solution of C60 is there, and when we have large number of these double bonds, and it is basically going for the corresponding one such double bond is going for the epoxide formation. So, that is also colored. So, if we just go for certain amount of epoxide formation, this is also colored there. But in this particular case, we do not have, like this potassium permanganate, we do not have d electron in the system, but still these are colored. So, why it is colored? So, we have this particular bonding for any carbon-carbon double bond system. We know that one bond is formed from the sigma bond and another is due to the pi. So, once we have any electronic system and any structural system, we have the corresponding bonds made up of sigma and pi. That means electrons are localized by forming two bonds, one is sigma and another is of pi type. The type is only different. We can have the corresponding antibonding levels which are pi star and well as sigma star levels. So, involving these levels, these are now our new electronic levels. Which are involved in transitions. So, if these sigma, pi, pi star and sigma star orbitals are utilized for these transitions, we will find that though we do not have any d electron in the system, that means the question for any kind of dd transition is no more. So, we have some other type of transitions, but what we will see that in the other case, that means when no d electron is present, such as manganese 0 system, but we can have some charge transfer type involving, if the ligand system is there, if the organic part is there, we can have some transition involving these levels, but there are some transitions where the metal d level, d electron is not there, that means the electron cannot go from the d level, but this 0 means it is a vacant level. So, we have 5 vacant levels. So, they can be very good acceptors instead of donor. So, we can have very good acceptor levels on the d level which is vacant in electron. So, we can only accept the electronic charge density from the ligand system or any other oxide system to those orbitals such that the corresponding transition or the charge transition can take place. So, in such transition metal complexes, a change in electron distribution between the metal and the ligand can give rise to the corresponding charge transfer bands. How we get that? So, these levels involving the metal as well as the ligand. So, these charge transfer transitions basically we see in the UV visible region. UV visible region means we have a high energy region, that means beyond 400 or 420 nanometer, less than that, and they are highly intense because the corresponding energy values, that means E1 and E2 are very high compared to the DD transition. And just now what I told you, that the corresponding epsilon values are also very high, and these epsilon values are of 50,000 liter mole inverse centimeter inverse or mole inverse per centimeter inverse, and in this particular case, and the selection rule is definitely be allowed, because we are not talking in terms of the corresponding DD transitions. So, why we see a high intensity in these charge transfer bands? The intensity of the color is due to the fact that there is a high probability of these transitions taking place. So, we will have very high probability of these transitions to take place, and selection rule for the forbidden DD transition result in weak absorption, but this selection rule no longer operating for these charge transfer transitions. So, as a result, for when we see that a particular octahedral complex can give an epsilon value of 20 mole inverse centimeter inverse or less. That is why in case of cobalt compound, what we have seen, that these epsilon max values are less. So, it is very difficult sometime when the epsilon value is around 20 or less mole inverse centimeter inverse for a typical transition where delta E value is very small. So, sometimes we cannot detect it also, and for that good detection we need highly concentrated solution, and sometime higher path length of the cell. So, these are the two things where we can nicely detect a very low concentration, very weak DD transition, which can be measured by using a spectrophotometer of good solution of high strength. Thank you very much.